All right, so let's complete our derivation of the partial derivative. And I hope you will also have a chance to attempt the quiz that we have along with the modules for you. If you have any questions, feel free to book a session with me for a one-to-one discussion. So we have the change in the temperature or the total change in the temperature as T, the temperature field, measured at x plus dx, y plus dy, comma, z plus dz, minus the temperature field at the point x, comma, y, comma, z. And what we were interested in is to figure out a way that we can measure or we can capture this tiny change in the derivative, tiny change in the value of the temperature using partial derivatives. So let's see how we do that. So let's add and subtract a few terms here. And we've already added and subtracted one term in our previous video. So let me just do that again. So I'll add t x plus dx, comma y plus dy, comma z, and I'll subtract the same term, which is x plus dx, comma y plus dy, comma z, and I'm going to add another term, which is x plus dx, comma y, comma z, minus x plus dx, comma y, comma z. And now let's combine some terms. So let me use another marker. So let's pick out this term, which is one of the original terms we had, and we'll subtract this term from it. These two together would give us the partial derivative of t with respect to z. This is what we talked about in the previous video. Now let's look at another combination. So we also have this term right here, where x plus dx, y plus dy, comma z, and then we have this term. Can they be combined? We have x, which is changing, x, which is constant, sorry, y, which is changing, and z, which doesn't change. So perhaps we can combine these two terms, right? And let's see what we can make out of these combinations. So we'll come back and I'm going to first combine these two terms and write, or rather divide and multiply this expression with dz. So I have y plus dy, comma z plus dz, minus the temperature at x plus, let me just write it on another line. So we have minus temperature at x plus dx, comma y plus dy, comma z. And for this combination, I will divide by dz and multiply by this. So that's one combination we have. Then we have, what else do we have? We have x plus dx, y plus dy, comma z. And let me try and combine it with this. Does it make sense? So t x plus dx, comma y plus dy, comma z, minus t x plus dx, comma y, comma z. If I look at these two terms, x plus dx is same, z is same, and it's only y that's changing. So I'll perhaps divide by del y, or perhaps divide by dy and multiply by dy. So that takes care of this term, this term, this term, and this we combine with this we combine with this. Now we have these two terms remaining. So we have t x plus dx, comma y, comma z, and we already have a term which is t x, comma y, comma z, which was a part of the original term that we had, right? And if you look at the arguments for these two sort of functions, we have y, which is the same, it doesn't change, z, which is the same, which doesn't change, and x changes from x to x plus dx. So if I divide this by dx and multiply by dx, I have all the ingredients that I need to rewrite this entire expression, the total change in the temperature field in terms of partial derivatives. So this particular combination will give me, or rather, this particular combination will give me d dou t. That's the notation we introduced last time. Dou z dz. That's this combination. Let's look at this combination. Here, y is changing. That's the only argument that's changing. So that gives me dou t Tau y, dy, and in this combination, only x is changing. So that's tau t, tau x, dx. And that's the total change in the temperature, expressed in terms of partial derivatives of the temperature field with respect to each of the independent variables, x, y, and z. So hopefully that gives you some sort of introduction to the idea of partial derivatives. In the next video, I'm going to rewrite this expression in a way which will introduce, or which will allow us to introduce, an interesting mathematical character known as the dead object. We'll see you next time. Thanks.